All right, hello. Happy Wednesday. Let's dive right on in. Today we're going to be talking about reaction order and the rate constant. And as I said, today is going to be a very meaty lesson. So by the end of today's lesson, you should be able to say that I can use experimental data to calculate the reaction order for reactants. And I can use experimental data to calculate the rate constant of a reaction at a constant temperature. As per usual, let's start with a little warm-up. What is the overall order for the following reaction? 2NO plus O2 yields 2NO2. Rate equals K times concentration of NO squared times concentration of O2. Hopefully, you are saying that this is a third order reaction because we've got an exponent of 2. So that means that the concentration of NO is exponentially related to the rate, while the concentration of O2 is directly proportional to the rate. And it has an exponent of 1. And we add 2 and 1 to get 3. So today, when we're talking about the overall reaction order and rate law, determining those experimentally, the first thing we're going to do is we're going to play around with some formulas, because I think that if we talk about the formulas first and then we add in some experimental data numbers, it will be easier for us all to understand. So first off, when we are looking to determine the rate order of a specific reactant within a reaction, as I think I mentioned it yesterday, when we're looking at our experimental data, we're going to have usually 3 to 4 trials of an experiment where the temperature is constant, but the experimenter has varied the concentrations of each of the reactants. And when we look at that, we want to identify similarities in concentrations as well as differences in concentrations, and then differences in the initial rate, which is an instantaneous rate that we're going to get from the data. But basically, what we want to do is we're looking to find these exponents. We're looking to find M and N, because remember, that's the reaction order. So to do that, basically what we're going to do is we're just going to take the data from 2 of those reactions. In this fictional example, I've used the reaction number 2 and the reaction number 1. And I'm going to be looking to isolate for M, to solve for M, so that I can determine what the reaction order for reactant A is. And we'll see this better when we're looking at it with data. But usually you want to choose something where you've got different values for one reactant, but for those 2 trials of the experiment where you've got one reactant that was varied and one reactant that was kept constant. And so in this fictitious example, we're pretending that the concentration of B was the same in reaction 2 and reaction 1. So that means that we're going to be able to cancel them out. And so our data, or our formula is going to look a little bit simpler then. So we've got the rate 2 divided by rate 1 is equal to the concentration of A in reaction 2 to the M power divided by the concentration of A in reaction 1 to the M power. We're also canceling out, we also cancel out our K's because K is constant, so that means it's going to be the same. A number divided by itself is always 1. Let's keep on forging ahead. Basically, because we've got a denominator and a numerator that have the same exponent, we can take that exponent out to the side, and that's going to help us in our next step. Ooh, we've got a little bit of a lot going on here, but that's just fine. So I just pushed everything together right here so that we could see all of that together more clearly. Got rate 2 divided by rate 1 equal to concentration of A in reaction 2 divided by concentration of A in reaction 1, all of that to the m power. And in order to solve for m, we're going to have to take some logs. So we take the log of both sides, and then we can divide both sides by the log of concentration of A in reaction 2 divided by concentration of A in reaction 1. And that will allow us to isolate m and to find the value of m, or our reaction order. I know that seems like a lot, and I know that I said it would be much more clear when we've got our data. So here is me promising, or acting on that promise. Here we've got some data. For the reaction H2 reacts with 2NO to yield N2O plus H2O. As I said, we've got 4 different iterations of the experiment. Here in column 1, we have our initial concentrations of hydrogen. So as you can see in reactions 1 and reaction 3, we had the same concentrations. And then in reactions 2 and reactions 4, we had the same concentrations. So that means 1 and 2 and 3 and 4. We've got some pairs that we can work with. Here's our initial concentration of our reactant NO. And here we can see 1 and, experiment 1 was the only time we see a concentration of 0.5000 moles per liter. Otherwise, we've got 2 reactions where we've got the same, and we've got a third that has a different one. And here is our initial rate. So think back to Monday when we were talking about rates. We talked about the average rate of a reaction, but we also talked about taking the tangent line at specific points to find specific rates. And this is an example, and I talked a little bit then about how using the initial rate is something that we often do, because when a reaction is just starting out, we kind of assume that we are working with all reactants and no products, because if you take that initial rate, if you're able to find the tangent line just as the reaction is beginning, you haven't had time for anything to produce, for any products to be produced yet. So these are our different initial rates for each of the reactions, for each of these experiments. And it does not say this, but it should. All of this is occurring at the same temperature. Experiments 1, 2, 3, and 4 all occurred at the same temperature. Otherwise, they would belong in different data tables because K, our rate constant, is dependent on temperature. So what's the first thing that we're going to do here? Well, let's find the order with respect to NO. Now remember, order has nothing to do with stoichiometric coefficients. What we're going to have to do is we're going to use that formula that we just figured out on the previous slide, and we're going to use that to figure out the order. So like yesterday, we were given a rate, and then, or a rate law, and then we, from that, determined the order. This time, we're going to do it with our experimental data. So what's the first thing that we're going to do? Well, the first thing that we're going to do is we are going to look and see if there is 2 sets of data where we have different initial concentrations of NO, where there is also where the concentrations of H2 are the same, because remember, we want to be able to cross out those initial concentrations of H2 so that we've got a simpler equation to work with. So let's see here. Nope, that one doesn't work out very well. That one doesn't work out if we compare it to 1, but let's see. Ooh, what if we use 2 and 4? Because I've got differing concentrations of NO, but I have the same concentration of H2. Let's do that. And for simplicity's sake, I am also going to block out 1 and 3 right now, just so we don't have to stare out too many numbers. We're using experiments 4 and 2. We've got a nice, tidier looking screen right now. So the first thing we're going to do is we're going to set our, we're going to set up our equation. So remember, we've got, now we're using experiment 4 divided by experiment 2. So we will have our initial rate for experiment 4 divided by our initial rate for experiment 2 is equal to the concentration of, well, would you look at that? I've put that in the wrong order, folks. It should say the initial concentration of NO4 divided by NO, the initial concentration of NO for 2. So this should be 0.6 thousand divided by 0.3 thousand, all to the nth power. And that n is what we're looking for. Remember, we're looking for the order. So we're going to solve for n. We've got some beginning numbers to work with. I promise my calculations are correct. I've just flipped my numbers around when I was writing them. My apologies. So let's simplify these numbers down as much as we can for now. Oh, that looks much tidier, doesn't it? When we divide 7.37, 3 times 10 to the 6th by 1.843 times 10 to the negative 6th, we get 4.001. And when we divide 0.6003 by 0.3000, we get 2.0 to the nth. So now we're going to have to, here, you could probably work this out on your own what n is, but it is good to practice using our logarithmic bases. So let's solve for n. N is going to equal the log of 4.001 divided by the log of 2.000, which means that n is equal to 2. So if n equals 2, that means that the concentration of NO is which order? It is second order. All right. We know the order for NO. Let's find the concentration, the order for H2. So we're going to do the same thing. I'm going to look through the table to see if I have two instances where H2 has different concentrations, but NO has the same concentrations. This is going to be a little easier because there's only 2 times where NO has the same concentration. So we're going to use experiments 3 and 2, or 2 and 3, and I'm going to block out 1 and 4 again. All right, so we are going to start off by setting up our equation again. So we're going to divide our rates. We're going to divide the rate for experiment 2 by the rate for experiment 3, and set that equal to the initial concentration of H in experiment 2 by the initial concentration of H in experiment 3 to the m power. And once again, we're solving for m. This time I have my numbers correct, I promise. So let's simplify those numbers down a little bit again. And isn't that much prettier? We've got 2.000 is equal to 2.000 to the m. This one should be real easy to figure out what that m is, but let's set up our logarithms again anyway. M is equal to log base 10, 2.000 and divided by log of 2.000. You should realize that m is equal to 1, which means that H2, the initial concentration of H2 is a first order. All right, so we know the order of both of our reactants now, which means that we are actually incredibly close to being able to finding the overall reaction order and then solving our rate constant. So we'll be able to figure out what K is. So once again, let's look at our overall rate order. We just decided that the overall order, pardon me, once again, I have put things in the wrong order, friends. The concentration of H2, that should not be a 2, that should be a 1, because that was a first order, and the concentration of NO was a second order. We will still have the correct overall reaction order, but I have put things in the wrong place. My apologies. Our reaction order is 3, which means, of course, that this is also wrong. Our rate is equal to K, concentration of H2 times the concentration of NO to the second order. let's work on figuring out our rate constant. Once again, I apologize. I have put the wrong power in the wrong place. It will not affect our ability to calculate the rate constant, however. So we just use this formula. Rate equals K times concentration of A to the M power times concentration of B to the N power. Here we've got subbed in our two reactants, and we'll actually be able to solve, for K this time. But we're going to use one of the initial rate values, and I will actually pull some numbers from this chart just to fill it, but we're not going to keep flipping back and forth for simplicity's sake. But we're going to use an initial rate as our rate, and then we're going to use the initial concentration of both of our reactants from that same experiment to calculate K. So let's plug in some numbers. Oh, actually, let's flip that around first. So if we solve for K, we've got rate divided by concentration of H times concentration of NO squared. Then if we plug in some numbers, you'll see here that I chose to use that very first rate. So I just take that rate divided by the concentration of H2. And once again, that is not squared. When I did the math correctly. I typed this wrong. Times the concentration of NO, so 0.1000 squared. And when we do the math, we punch some numbers into a calculator. We find our constant, our K, is 1.024 times 10 to the negative fourth liters squared per mole squared times seconds. And actually, we are going to use this moment to transition into talking about units for K, because as I've mentioned before, this constant has units, and the units depend on the order of the reaction. So if we have an overall order, a reaction order of 3, as we just saw, we're going to have liters squared per mole squared times seconds. But for a 0 order reaction, we're going to have moles per liter times seconds. For a first order reaction, we're just going to have 1 over seconds, or s to the negative first. A second order reaction is going to have liters per mole times second. And as I said, a third order reaction is going to have liters squared per mole squared times seconds. So it is important to make sure that you have the correct units for your reaction order. That's a good way to check and make sure that you are on the right track if you're not sure. But hopefully that was a good way to weave together everything as far as using experimental data to calculate our reaction order and our rate constants. If you need to feel like you need a little bit more on this topic, feel free again to contact me. Otherwise, I would suggest reading the textbook, chapter 16, section, let's see, 16.3, and yeah, 16.3 covers a lot of this as well. But as I said, feel free to contact me, and I'm happy to answer any questions. I will see you tomorrow.